I've been honored with the task of introducing Professor Willy Herroelen, which, as many of you know, and surely those which are involved in scheduling and project management know him, but probably not many of you have got the opportunity to listen to his lectures and the way he communicates. I think it has been a very good idea to have him to close the conference, no? Willy, if I may say so,
yeah, sure.
Has a breathtaking and astonishing academic curriculum vitae, not only for what he has contributed so far, but for the expected contributions I'm sure he will make in the future. Now, as an emeritus professor full of energy, as you can see. He obtained his Ph.D. in applied economics at the Catholic University of Leuven, where he started his academic career as an assistant research in 1972, being promoted for professor in 1984, and is actually emeritus professor of operational management at the Research Center for Operational Management of the Department of Decision Sciences and Information Management at the Faculty of Business and Economics, Leuven.
Yeah.
From his early works in the early 70s, I may quote one which mainly, I wouldn't be surprised if he doesn't remember. The use of heuristic programming in management science in 1970 with the short English translation. Because this has been the topic which he has been working with all along his very good academic career. Heuristic methods for multidimensional, the knapsack problem in 1974 was another landmark in the way he conformed his curriculum vitae. His research domain has been operational management, in particular planning and scheduling under resource constraints. His current research interest is in project planning and scheduling under uncertainty, robust and reactive dynamic planning, within the broader area of resource-constrained project planning and scheduling as applied to management. He is past editor of Management Science, senior editor of the New Product Development R+D and Project Management for Production Operation Management, POMS, is guest associate editor for Manufacturing and Service Operation Management, is area editor for Project Engineering and Management for Computers and Industrial Engineering, and he is a member of the editorial board of cutting-edge journals like the International Journal of Production Research, the Foundations of Computing and Decision Science, and the Journal of Operation and Logistics. So for those of you which are young teachers and try to promote and publish in leading journals, I think he will be very helpful probably. So thank you very much for this opportunity.
Yeah,
sure. He is author of 2 international-oriented books, one of them known by anybody which has dealt and studied project scheduling, and has been author of 6 scientific books, and has got more than 15 articles as part of good chapters, relevant chapters on the field, published by internationally oriented publishers. He has got 60 articles published in international leading journals. And he's still publishing, because this year, for instance, he is, or is due by now, he has already published, or is in the process of publishing, 4 important and relevant articles, again, in very top standard journals. So he's a very peculiar emeritus professor, full of energy, and I'm sure in his private life as well he does things as well as does in academic life. Mm-hmm. But this part of the curriculum vitae I'm not authorized to discover, so I wouldn't say anything. But just perhaps he likes traveling, normally not alone, and photography, which is a way to enjoy again back his traveling. I give my congratulations to the workshop organizers, led by Adolfo López Paredes and Javier Pajares, these two chaps which are over there, for giving us the opportunity to hear the plenary session by Professor Herroelen and the chance to the young people to meet him now and later on. I think it's time for me to say, please take the chair.
Thank you.
Thank you.
Ladies and gentlemen, good afternoon, almost good afternoon. In Belgium, this is already afternoon. I am very delighted to be here, and I'm very honored by the invitation. This is the first time that I am in Valladolid. I thought that Leuven was an old university, 1425, but I think we have been outperformed by almost 100 years. So I grasped the opportunity to give you a little bit of an idea about the things that we have been doing over the recent years in the area of project scheduling and resource constraints and in the presence of uncertainty. Ladies and gentlemen, I don't know whether you know the American Production Inventory Control Society. They have what they call laws of project management. And one of the laws says there is no single project in the world that was finished on time and within the budget that was originally conceived for it. Now, when we take a look at this list, very famous projects throughout the world, and by the way, some of them are missing. The Cathedral of Valladolid is not on it. The Sagrada Familia in Barcelona is not on it. I mean, if I take a look at this, I am convinced that that law of the American Production Inventory Control Society may be correct. It's amazing that so many famous projects, last example the Airbus 380, are not finished on time and almost always exceed their original budget. This is an example that you should know because it's the Berlaymont building in Brussels, Belgium. That's the building where the European Commission meets when they are having dinner and lunches in Brussels. Okay? And in 1991, the building did look like this, and they detected asbestos in the building. Now that's very dangerous stuff. So they decided, okay, let's remove the asbestos and let's renovate the building. The decision to do that was made in 1991, and the project should be finished 1998. Okay? Now you see, it took them more than 6 years to sign the contract. I'm not talking about politics, but this is what you could call not a short period of time. Okay? And our Prime Minister, anticipating the fact that, in July 1, 2001, Belgium was about to be the presidency of the European Commission. And our Prime Minister, Guy Verhofstadt, anticipated that. And just before Christmas 1999, he said this project is going to be finished by 2001. Obviously it was not. Okay? Now if you take a look at the right hand side there, this was the original budget. Okay? And this was the budget published 3 years ago, the total cost. So you see the project not only had a serious delay, but the total cost for the renovation only almost exceeded the original budget 5 times. And my poor country was condemned 3 times in a row to pay a penalty of more than 220,000 euro because the project did not finish on time. Okay? Project delays cost a hell of a lot of money. Right? Now, this is amazing because how come that projects always are late and run out of their budget? Because we have the Project Management Institute, more than how many thousand members worldwide. We have the project management body of knowledge. We have project management software packages. How come that projects always fail? Now, if you take a look at the literature, there are many reasons why projects fail. One of them is corruption. One of them is politics. Okay? One of them is very bad management. But if you look at the reasons why projects may fail, it often is the case that one of the major reasons is bad planning and bad project control. Okay? That appears in many of the cases. So project planning, project management is very, very, very important. It's a critical failure and success factor. Now, we did a survey in Belgium, the Netherlands, and also in the UK, trying to find out, because we do have project planning software, are project managers using that software? Okay? Now, the results were extremely disappointing. And I think the situation did not change since 2001. The two conclusions that came out of that survey in the various industrial sectors that you see there, especially in construction, the two conclusions are very, very, very disappointing. It appears that project planning software is very often not used to optimize. Okay? It is used to communicate. Look, this is our project. And you put the Gantt charts on the wall, you know, look how beautiful this is. But it is hardly used to optimize, to derive the best possible project plan. And very important, the people who are running around with those Microsoft project packages and Primavera and SureTrack and what else, they have very, very, very limited knowledge about the algorithms that do exist for scheduling projects and how they have been implemented in that particular software environment. So that's very disappointing, because the problem that we are facing is a very, very, very difficult one. Okay, we have been talking today about projects and about programs and about portfolios. If you take the essential building block, a project consists of activities, right? And activities have a duration, they take time. That's the first component, time. In addition, the activities are suffering from precedence relationships. Now, sometimes they are very simple, like finish, start precedence relationships with a time lag of 0. But sometimes we allow activities to overlap in time in very tricky manners. So that are the precedence relationships. Third element, activities not only take time, but they need capacity, they need resources. Human resources, workers, machines, materials, subcontractors, all different type of resources. And whether we like that, yes or no, those resources usually have very limited capacities and are very expensive. There is an example in Belgium a few weeks ago, you know, in the port of Ostend, they finished the windmills that will be placed in the middle of the North Sea to generate electricity. Now, in order to take this thing to the spot in the North Sea, you need a very huge, expensive crane to do that. Okay? And that crane needs to be reserved almost years in advance, because there is only one such big crane in Europe. But it came one day too late. Okay? That cost an enormous amount of money to the company, because that crucial resource was not there when it was supposed to be there. Now, those four guys, obviously, they interact. We want to start an activity of a particular project, and we cannot because the predecessor is not yet finished. Or we cannot start it because we don't have the sufficient manpower to do so. So those four elements almost always run in conflict. And whether we like that or not, what complicates the issue is this. Many projects have to be performed under severe uncertainty. And when we think that things go right, you know, this fellow comes along, Mr. Murphy, and he always causes problems. We think we have everything under control, people go on strike. We think that our subcontractor is reliable, and he doesn't show up on Monday morning. So we are living in a very, very, very complex situation. Let's illustrate that by a simple example. Okay? Very simple project. 10 activities, 1 up to 10. Number 1 and number 10 are the dummies. So on top of each activity you have the estimated duration. So activity 6 has a duration of 3 months, let's say. And every time period we need 8 workers to do that activity. Okay, so we assume one single resource type. And that resource, we have 10 workers available every day. Let's take that as an example. And the relationships are finish-start relationships with a time lag of 0. So activity 8 can start as soon as activity 7 and 5 and 4 and 1 are finished. Okay? That's a problem. I am the poor project planner. So what do? I use commercial software, right? But before I do that, I remember that CEPMaW'08 says, in order to estimate the duration of a project, you can compute the critical path, okay? The longest path in the network. I have colored it in red, okay? 2 plus 2 plus 3 plus 4, that's 11. Critical path length, 11 months. Okay, I go to SureTrack, and I say to SureTrack, plan that project. I am a naive manager, so I just click on the default option of that software package. Okay? So what comes out of it is what we know as an early start schedule. So the 10 activities are started as soon as possible, satisfying the precedence constraints. Right? No problem. And you see what happens? The project duration indeed is 11 periods. But in the first 4 periods, this plan needs more workers than the 10 workers that we have available. So this is not feasible. Okay? We cannot do it because here in the first 4 months we need more than 10 workers and we only have 10 workers. No problem. I can play around with SureTrack and I ask the package, okay, generate a feasible schedule that satisfies the precedence constraints and that satisfies my capacity constraints. Okay? Now, like I told you, I am very naive. My mother always told me, never do tomorrow what you can do today. Okay? I'm a good house father. So I click on SureTrack and I say, okay, generate me a plan using, in order to resolve that resource conflict, using what is built in standard in the software, the early start heuristic. Okay? So the software will create a list of those 10 activities in increasing order of their earliest start time, coming out of the critical path analysis, and will generate a plan. And I get an heart attack. Because my original duration was 11 months, okay? The software tells me 20 months. That's almost twice the original duration. I can do better. So what do? SureTrack, kick it out. Okay? And let's use our own software. You know, we developed there in 1992 a branch and bound method to generate optimal schedules. Okay? And I will show you, if we have the time, I will show you in the software how this can be done later on during my presentation. You can use the software for free if you go to our website and you click the name Rescom. You can download the software and play with it. Okay? The only thing that I ask you is, if something goes wrong, tell us. If you see ways to improve it, tell us. Okay? But you don't need to pay. But you can pay. But okay. So I use that software and I generate my plan. What comes out of it? Big surprise. The software says not 20 periods, only 11. That's very strange. Okay? So that software managed somehow to generate a feasible plan with a duration of 11 months. Now let's look at the resource profile. So there you see my 11 months, and these are my 10 workers, and these are the activities. And that's a resource capacity profile. And you see the accounting department, ecstasy. I manage over the 11 months to achieve full capacity utilization. I will be promoted, right? Now, if Elio Goldratt takes a look at this resource profile, he should be very, very nervous, okay? Because he says, it is not the critical path that determines the project duration, it is the critical chain. Ladies and gentlemen, how many chains in this stupid example determine the duration of 11 periods? You see, by pure accident, I have 4 blocks of 2 activities That means there are 16 different sequences of activities that will determine that duration of 11 months. Okay? For instance, activity 5, followed by 3, followed by 8, followed by 9. It can also be followed by 2, or activity 3 can be followed by 5, and that one by 9. So I have 16 different critical chains. Which one is going to determine my project duration? Okay? Second, if I say, okay, Herroelen, you did a fantastic job, applause, because you managed to have an optimal solution with a duration equal to the critical path, I should be very careful. Because you see, this is what we call a tight schedule. There is no idle time anywhere in that schedule. That means if one of the activities is delayed for one reason or another, my project will be delayed. Yeah? If on Monday morning, out of the 10 workers, only 2 show up because Barcelona did lose the game and they are suffering from psychological diseases. Okay? So if I don't have the capacity available, I will be in trouble. Okay? Under uncertainty, this schedule is a very stupid schedule because the slightest disruption will kill my plan. And those disruptions may be of several different types. Okay? Activities may take longer or shorter in duration. That's classical. They may suffer from delays. The subcontractor does not show up on Monday morning with his material. Or his truck breaks down. Or the truck drivers go on strike. Okay? The resources may become unavailable for several different reasons. Machines may fail, workers may go ill, material is not delivered on time. We may have quality problems. I mean, it's also possible that the scope of the project changes over time. We have to add additional activities. Some of them may not be needed. I mean, it's a dynamic world. And all those possible disruptions, yeah, they may create delays in the project, obviously. They may result in the fact that we don't meet that due date that we set forward. We said the project will be finished in 11 months, but it cannot. It's possible that the plan is no longer feasible because it violates some of the constraints. It is possible that we have cost overruns, and above all, and that's very, very, very important, it was mentioned in the previous sessions, we have projects, we have programs, we have portfolios. There is more than one project that we have to do, and all of them have their own supply chain. So if there is a disruption, that disruption propagates throughout the supply chain and nobody knows what we are doing anymore. Okay? We expect a delivery from Spain in Brussels and the ship does not come. Problem. But when the ship does not come, we cannot do a lot of projects. So it's a propagation thing that we have to stop. What can we do? Well, the Belgian solution is simple. Do nothing. Okay? That's what we call the Belgian compromise. Let things go. But that's not the best solution, believe me. So what can we do? React. If there is something going wrong, react. That's what I call from now a reactive scheduling strategy. Now we can do two things. Either we create a plan, and when the plan is disrupted, we generate a new one, or we repair an existing one. That's one thing that we can do. Or some people say, in an uncertain world, it is impossible to plan because we don't know the duration. We don't know the required capacity. We cannot plan. That's what I call here no baseline schedule. We don't create a plan in advance, but when the project is running, we make our decisions dynamically over time. That's what I call the use of no baseline schedule. What else can we do? Well, we can create a plan and then protect it against the things that we think that might go wrong. Okay? That means, ladies and gentlemen, that we need to perform very, very strict risk analysis of our projects. The Belgian Building Research Institute is currently maintaining a huge database in which they store for common construction type of activities, the type of risks that may happen, the various risk factors that have occurred in the past, together with their impact on the duration of the activities, on the probability of meeting delivery times and things and so on. Because even in construction, not everything is unique. I mean, it's not the first time in history that someone will paint this ceiling. Okay? It's not the first time in history that someone will install electricity in this building. So there is a lot of experience going on. That means we need to perform a risk analysis, and given that, we want to protect our plan against the things that we think that might go wrong. Right? And if that protected plan breaks because the disruption is too heavy, only then we repair or reschedule the plan. So that's the idea. That's what I call their proactive reactive scheduling. The idea is to create a schedule that is robust. That means if we say this activity will start on Monday, then we hope that we can start it on Monday. And in the ideal situation, it should start on Monday. Okay? That's the idea. Now, let's first say a few words, very few, about that stochastic thing, stochastic project scheduling, where we assume that it does not make sense to create in advance a plan. Okay? That means that at stochastic points in time, corresponding to the completion of activities, we have to decide during the construction work of our project what to do next, dynamically over time, because we don't have a plan in advance. Okay? That means we have to take decisions at a random time instance. And in doing so, we have to satisfy constraints, obviously. That means if we decide, okay, now today we can start a number of activities and we are going to start this one, then it must be feasible. We must satisfy the precedence constraints and the resource constraints. That's what I call, sorry for that difficult word on this afternoon, an admissibility constraint. But that's not enough. We must also satisfy the non-anticipativity constraints. What the hell do we mean by that? That means I only know the past. Okay? I don't know exactly the future. I can only try to estimate or to make a forecast of things that can happen in the future. That means I can use probability distributions, or I can use fuzzy activity type of distributions. What else? I can only predict things. That means I need a dynamic reactive scheduling policy. What do I mean by that? Okay, let's take an example. 5 activities. Okay? This one has to wait for this one, and that one has to wait for this one. Okay? And now you see 3 colored sets. What I assume here is that activity 1 and 5, although they cannot be scheduled together, they can because there is no precedence constraint between them. The reason why they cannot go together is that both of them would need more resources than we have available. Okay? Same thing, the red set, 2, 3, and 4, there is no precedence relation between them, but we cannot schedule them together because the 3 of them need more workers than we have. So here in this example, I have what I call 3 minimal forbidden sets. Activity 1, 5, 2, 3, 4, and 2, 4, 5 cannot go together because I don't have the capacity. Okay, I don't generate a plan in advance. So what I'm going to do now, I'm going to apply, for instance, an early start policy. What does that mean? For each of those 3 sets there, I have to break that forbidden set by delaying at least one activity by another activity from the set. And I have to do that for each possible realization of the activity durations. Let's take an example. Assume that I have 5 activities. I assume independency of their durations, uniformly distributed in this example. variance of 2, and these are the estimated durations. Okay? And I assume now that in reality, these are the durations that occur. Okay? That means I observe my project, and what happens, the first activity has a duration 3, 5, 3, 5, 6. What is an early start policy? If I now decide that activity 5 must wait until 1 is finished, and 3 must wait until 2 is finished, and 5 must wait until 4 is finished, I break those minimal sets. Because you see, if I now implement that decision, 5 has to wait until 1 is finished, okay? But 5 also has to wait until 4 is finished, and 3 has to come after 2. This will be my plan, my schedule in reality, okay? So I did not build that plan before, I am building it when I am performing the project, dynamically over time, at each decision point, okay? The question is, does this work? Do we need an initial plan? Well, it's always safe to ask wise people their advice, okay? You know that guy, that's Henry Gantt. He developed the Gantt chart. So if you ask him, do you need a plan? His answer will be yes, obviously, for many different reasons. We needed to allocate our resources. We needed to code due dates to determine when things will be finished. Okay? We need to communicate inside and outside our supply chain, tell the contractors when they have to make deliveries, tell resources inside the company when they have to be available. We have to communicate. We need to organize ourselves. Okay? We need to make cash flow projections because we don't want to run over our budget. So for many different reasons, we do need a plan initially because we also want to measure our performance and to control the project. Okay? The problem is, how do we generate such a plan? Okay? How do we generate an initial plan and how do we protect it against possible disruptions? That's our problem. So we want to create a baseline plan and then protect it against the things that we think that might go wrong as a result of our risk analysis. Okay? My objective function, well, I first want to create a plan that gives me stability. That means if the plan says that activity is going to start next week, Monday, then in reality, I hope that that activity indeed starts on next week, Monday. That's what I call solution robustness or stability. Okay? Second thing, the plan should be a good one. I mean, the project duration, for instance, should be as small as possible. Okay? That's what I call quality robustness. And third, if things go wrong, it should be possible to take corrective action. I mean, I should be able to react when things go wrong. That's what I call flexibility. Okay, fantastic. We had a workshop at the University of Tours 2 years ago. And our objective during that workshop was, how do you measure this? How do you measure robustness? Okay? And after one full day of hard work and a very nice lunch, our conclusion was, we don't know. How do you measure that? Because you can use several different measures for different types of robustness. Okay, I'll explain 2 of them. This is my baseline plan, and this is what really happens when I do the project. That's the reactive schedule, or the realized schedule. So my objective function is now the following. This was the planned starting time of activity J, okay, in my plan. This is a random variable. This is the actual starting time of that activity when I do the project, okay? So you see, I can start the project earlier than planned, or later than planned, or exactly on time, okay? So I take the absolute difference between those two, and I multiply it by a weight, Wj, which gives me, economically spoken, the marginal disruption cost. What do I mean by that? That means I ask the project manager, that activity over there, is it critical that if we plan it to start next week Wednesday, that it actually starts next week Monday, or do we just don't care? So as a result of our risk analysis, we try to come up with that inflexibility weight. I mean, if W is a high value, then we think it is very important that that activity starts according to the plan. If it is 0, we just don't care. Okay? And we want to minimize the sum of that product over all the activities. Now, you are going to say, Herroelen, you are crazy. And I agree that I'm crazy, because this is very difficult to measure. Okay? It depends, that minimization, on, first of all, on an estimate of this instability cost, or we take a surrogate measure. Okay? We don't measure it exactly, but we hope that we measure it correctly. Okay? You see, ladies and gentlemen, that's very important. If all the W's are 0, except for the last activity in my project, what I am doing then, I am minimizing the expected project duration, right? Okay? So I can combine things now. In addition to the previous objective function, I can try to compute the probability. This is the starting time of the last activity in the project, the dummy end. This is the probability that my project is finished within the due date, that it is finished on time or earlier than planned. And my objective is to maximize that probability. Okay? So you see, I can now combine the two things. I want to generate a plan that gives me stability. If I make promises and say this thing is going to start that day, well, I hope it will be starting that day. But at the same time, I want to finish my project within the time period that I planned. Okay? For the remainder of my talk, I will only consider uncertainty as far as the time is concerned. There are many different types of uncertainty, but I don't have the time to cover all of them. So I assume here that my risk has to do with durations and with time delays. Okay? Well, if you find an overview or want to find an overview of all those algorithms that exist and that we developed, I gave a tutorial at the Informs meeting in Seattle last year, so they are all in there, and I will be glad to give you that paper. There are two things that I will discuss now. The critical chain methodology, which has been already mentioned several times during this workshop, and a very simple thing that I will demonstrate on the software later on, which we call the starting time criticality method. Don't blame me for that nice word. Okay, Goldroute. You know that software. ProChain is one of the famous ones. It comes as an add-in on Microsoft Project. There is Concerto, there is Realization, many different types of software packages. So let's play the naive manager again. This is my example now. 9 activities. The first number is the duration. The second number, the resource requirement. Okay? That means activity 7 has an estimated duration of 2 periods, and every period it needs 3 workers, and I have 10 workers available. Okay? I do my homework. This is the critical pass. 5 plus 8, that's 13. That's an unlucky number. So that's the first warning signal. Okay? What is Elijah Goldroute telling us? Okay, we are going to generate a feasible plan, and in that feasible plan we are going to determine the critical chain. Yeah? That is the longest chain of activities that have to be scheduled one after the other because they are precedence constraints and or because they are capacity constraints. Okay? And you see the software here has identified those red activities as the critical chain. actually what the software has done, this is the critical chain that it found throughout that project network. Okay? That's the longest chain of activities that determine the project duration. Okay. The critical chain concept now says that minimal project duration here is 15 periods. But I'm not going to tell my customer that I'm going to finish it in 15 periods. Okay? I'm going to add, at the end, a project buffer. And I am a naive manager again. I take the manual of ProChain and it says you just take 50% of the duration of that critical chain, which means 50% of 15, that's 7.5. Okay? Round up, that's 8 periods. 1, 2, 3, 4, 5, 6, 7, 8, 9. Second art attack. Why the hell does he say 9 and not 8? Okay? So something is wrong, or something is going strange. What critical chain will do now is where the non-critical chain activities, and in this example this will be activity 1, 3, 5 and 8, where they meet the critical chain, the software will insert a feeding buffer. Okay? So there will be a feeding buffer there, and a feeding buffer here, and there will be a feeding buffer there. Agree? Indicated here by the green bars. And I then take the default option, 50% of the duration of that chain. So 50% of 4, that will be 2, and 50% of 9, that is 4.5, that will be 5. Okay? Third alt attack. What the hell is happening? I mean, the software inserts those feeding buffers, but you see he runs into problems in doing so because he needs to push those non-critical chain activities to the left to make some room for the buffers, and he doesn't succeed in doing that. You see, this buffer is already penetrated for 50%, and that buffer is already fully penetrated. So what's the use of those buffers? I mean, they don't serve any purpose anymore. And in addition, if I look to my stability objective function, this thing is not stable. I mean, the slightest disruption in one of those activities here creates a delay in that anticipated duration of 15. It will consume the project buffer, but it will create nervousness. Okay? So we should be able to do better. And let's see what we can do. You see, the due date here is not 15, it goes up to 24. Right? Okay. This instant, that are the data. So these are those marginal disruption costs, the resource requirements. This is the variability, high, medium, low, and that is disruption. So plus means longer duration, minus means shorter duration. What can we do? First thing, we can do something stupid. I use my optimal procedure that I showed you early. I generate a minimum duration schedule, okay? And look, the red chain of activities is not the same as what came out of the critical chain software, okay? The critical chain software said, this is the critical chain, 0, 2, 4, and then up and then down. Here it goes 0, 2, 4, 6, 8. So here, this is the critical chain, okay? And you see, just to play tricks, I put the due date on 20. I will come back later how we can set that due date, because that's an interesting problem, how to set due dates in the project. And we can use that buffer. But you see, it's still not stable. The slightest disruption here will create nervousness in my supply chain. So I don't like that. We can use heuristics. Okay? For instance, the serial schedule generation scheme using the latest start time heuristic. And by pure accident, by pure luck, it gives me exactly the same solution, right, as my optimal one. But again, I don't like it because it's not stable. Okay? So what can we do? we have a project running now at the Belgian construction companies, and if you go to the practical world, you know that better than I do. You must talk simple things, because otherwise people don't believe you and will not do what you ask them to do. So the idea is to come with a procedure that is simple, understandable by practice people, and that still works and gives good results. What's the idea? The idea is to measure stability through what we call the starting time criticality of an activity. Okay? Taking into account those weights and the variance of the duration of the activities. Okay? And how do we measure that starting time criticality of an activity? By the product of two things. Namely, how important is that plan, so the weight, multiplied by the probability that the actual starting time will exceed the planned starting time, that we have a delay. Now you are going to say again, Herroelen, crazy. Because computing this probability, mathematically and statistically spoken, is very, very difficult. Okay? The third problem is NP complete, right? Even in the absence of capacity. That's why we use simulation in software like RISC, for instance. So we make a number of assumptions. We assume that only one predecessor disrupts, okay, and that the predecessors of the activity themselves start as planned. That are two stupid assumptions, I agree, because in reality they will not be true. Okay? So what do? Very important. This is my input plan. Okay? And what you see there is my project network, but the colored arcs in red, they show how my resources are transferred from one activity when it finishes to the next. Okay? Let's clarify that. You see that activity 3 here needs 1, 2, 3, 4 workers. Okay? So in this plan, what I have decided is that when activity 0, that's my dummy starting node, so immediately at time 0, I transfer 2 workers to activity 3. Okay? And when activity 1 finishes here, I transfer another 2 workers and they will perform activity 3. So in total 4 workers. So those red arcs represent what we call the resource flows. Okay? So you see activity 2 needs 3 workers and immediately it gets it at the start of the project. Activity 4, where does those resources come from? Well, 1 worker when activity 1 finishes will start activity 4, and when activity 2 finishes, the 3 workers will also start activity 4. That are my resource flows. Now I need to make those decisions. Okay? Mathematically spoken, I can generate algorithms that will come up with such a feasible plan. Okay. Now what do? How do I measure my starting time criticality? Well, I'm going to compute the probability that an activity I disturbs the starting time of an activity J. And I'm going to illustrate that in that example for activity 6. Okay? So that's my activity 6. So what are the predecessors of activity 6 when they are disrupted that may cause a delay in the starting time of activity 6? Well, you see, there is a path in this network from activity 1 to 6. Okay? Activity 2 may delay the starting time of activity 6. Activity 3 also, because there is a path going from 3 to 6. Activity 4 may disrupt it. Okay? And activity 7, when it is delayed, will disrupt it. Now, if I have an idea coming out of my risk analysis about the probability distribution of the durations of those activities, I can compute the probability that the duration of activity J in reality exceeds the difference between the starting times of activity I and activity J and the longest path between those two activities in that plan. Okay? So you see what I do? Very simply, the starting time criticality is my flexibility weight multiplied by the sum of those probabilities. And I just ask the computer to do that. Okay? So my surrogate measure of my instability cost for activity 6 is the weight the manager has assigned to activity 6 multiplied by the sum of those disruption probabilities. And I take the sum over all activities in my plan, and this gives me an estimate of my stability cost of 16.93. Okay? And now I'm going to buffer, starting with the most critical activities. So I rank my activities in decreasing order of that value, and then I will put in front of that activity each time a buffer of 1 period. And I check, is there a stability cost improvement? Then I leave the buffer. If not, I take it out again and I take the next activity. So we can do that very simply here. Huh? Just go fast. We order the activities in the decreasing order of their starting time criticality. We insert a 1 unit time buffer in front of activity 6. You see a 1 unit buffer here. Activity 6 will be delayed by 1 period and activity 8 will be delayed by 1 period. We update those costs and we reorder the list and we continue until there is no further cost reduction. Okay? And what comes out of it, this was my deadline of 20 periods. Okay? And you see, I now create time buffers at particular points in time. Okay? But those buffers now, the size and their position, are determined by studying the probability analysis of my schedule. Okay? It is not just taking things and divide it by 2. It is not optimal because I made those assumptions, but the idea is to put those buffers at particular points in time such that I maximize the stability of that schedule and I guarantee that I do not exceed my planned duration. That's the idea. Okay? So we can then talk about reactive procedures, but I think the best thing that I do now is to go to the software and to show you how we can do that in practice. Okay? That software package is an educational software package that we are still developing. Okay? So this is the example I used earlier, right? My 10 activities, activity number, the duration, and the number of workers that I need. Okay? Now the idea is to do a risk analysis. That's a lot of work. I mean, I must find a project management team ready to do that risk analysis, because if they don't do that, I am lost. Okay? So I need to convince the project manager, give me some risk information on this project. Okay? So what I can do, if I click on the corresponding activity, so this is for activity 2, okay? So you see what the project management team said initially, the duration that I am going to use in my plan is 4 months, right? But you see, we can change that, right? The corresponding activity 2 in this example requires 9 units of 1 resource. Again, I can change that, right? And simulate different capacity allocation scenarios. Okay? This here is what I called the marginal disruption cost. So now I am going to sit together with the project manager and ask him, okay, activity 2, how important is it for you that this activity is started according to the plan? In other words, what do you think, economically spoken, is the marginal disruption cost if the planned starting time of that activity is not met in practice? So you see, if the manager thinks that the last activity in the project, okay, this one, that it is very important that it starts on the day that it was planned, he will increase that inflexibility weight. Okay? If the manager thinks that for this activity here, it is not important that it starts according to plan, well, I can increase or reduce that flexibility weight. Okay? So you see, for instance, if activity 2 is a crucial contractor, that means if that guy does not bring the material in time, then I am in severe trouble. Then I give a very high inflexibility weight to activity 2. But if activity 2 is just making a phone call to my secretary, I will give it a very, very, very low flexibility because I don't care if there is a delay on that activity. So you see, when I do the risk analysis now, and I try to find out what are the anticipated risk factors that may enter on the scene and what may be their possible impact on my durations, I can play around and simulate a number of possible scenarios. Okay? And if I then go to my database, I can use my own experience saying, okay, last year I did a similar activity in that city and that were the risks and that was the impact. I can use that previous information. So here as an illustration, because we use it to play tricks on our students, I simply assume a triangular distribution, right? And I can again play around with those parameters, okay? So I can simulate many different scenarios. Now what's the idea? As an output of my risk analysis, I now want to generate a plan that is not yet protected. Okay? Now, there are several ways of doing it. Let's go to that branch and bound procedure that we developed there in 1992. So I generate the corresponding schedule. Okay? And I include all types of procedures that are standard in the software, including the optimal one. It takes some time. The guy is computing now. So now he's generating a plan using many different procedures to do so. Okay? So you see, you remember, the optimal duration for that example was 11 months. Okay? Out of those heuristic procedures that are in the software, some of them, don't faint now and don't blame me, but some of them said, we are going to plan that project in 20 months. That means, ladies and gentlemen, if I trust my software and I use Primavera and I click, whoop, early start time heuristic, parallel method, maybe 20 months comes out of it, while there exists a solution in 11 months. So picking the right scheduling procedure is of tremendous importance. It can cost me millions of euros if I take a wrong baseline plan. Okay? Why would I plan for 20 if I can do it for 11? Now comes my risk analysis, and now I want to protect that corresponding baseline plan. So you see, this was my optimal solution. My resource profile was a duration of 11 period. Okay? And now I go to that starting time criticality method. Okay? Now it says, what method do you want to use for your initial plan? So I take my optimal procedure, I click OK, and it shows me something strange. The thing has been simulating. You don't know, but it has been simulating. What it has done is the following. It took that resource flow network and it generated 1,000 scenarios for the durations of all the activities and for the possible disruptions. And now it comes up with the probability that that project will be finished in that period of time. So you see, if I say I want to finish my project with 95 probability, a percentage of 95, my reasonable due date will not be 11, but will be 16, coming out of the simulations. But if I am confident and I say, okay, I don't need that high probability, I am confident that with 70% of all possibilities I finish that project on time, then the due date can be set to 15. So you see, now I can play with my desired service level. What is it that I want to achieve? What is my due date that I want to agree with my customer? If the customer is very conservative, he will say, I need a very high probability that you finish it on time. If timely completion is not important, I can decrease my service level. Okay? So given my desired service level, for instance 75%, it will show me the schedule. And you see the due date is set to 15 now instead of 11. And the algorithm that I try to explain, given the information that I got from the manager with respect to the inflexibility of the activities and with respect to those disturbances that may occur, given those simple two types of information, the software has introduced at particular points in time buffers. So there is a buffer here, there is a buffer here, and there is a buffer here. And those buffers should protect my plan against the type of disruptions that I anticipated in my risk analysis. If my risk analysis is wrong, this thing will be rubbish. Okay? So risk analysis is crucial. Given the anticipated risk, this schedule should be a schedule with high stability and with a high probability that I can finish that project in due time. Now, to conclude, ladies and gentlemen, because I don't want, well, I am already 3 minutes late, I apologize for that. To conclude, like I said, we followed a number of projects in Belgium. And this is a 5-story apartment building in Brussels. Okay? And the project was not too large. It had something between 500 and 600 activities. Okay? And we did the following. We said to the project management, okay, what type of software do you use? And they said, we use Microsoft Project. Okay? And they planned the project. And this is my total stability cost obtained for that project if the activities are scheduled according to MS Project. Okay? So this is the sum of those starting time criticality costs. Okay? If I use ProChain with the standard rule of taking 50% of the length of the feeding chains, that was the stability cost. ProChain, because critical chain evolves over time, there are many more sophisticated methods to compute the duration of your project and your feeding buffers. So if you take the sum of squares procedure, that will be the stability cost. If you use our stupid procedure, that was the stability cost. So you see what I mean, what happened there on that project was the following, okay? This was the MS Project schedule for the most important activities of that project, okay? So I don't know whether you see it clearly, but here are the bars in the Gantt chart, okay? And that was the planned completion time of the project. And now I simulate the disruptions that actually occurred during the construction of that 5-story apartment building. Okay? And I see what happens to this plan. So I start that simulation, and the black bars give you for each activity when it actually started. Okay? So you see, I don't know whether you agree or not, this was not a stable plan. The project was finished here while the plan said it should finish there, and almost every activity suffered from a delay. Okay? So the result is the deadline, severely violated, an unrealistic planned duration given by the green line, and extensive rescheduling during the execution of that project. Now, if you apply ProChain on the same project, you see what happens. ProChain is adding those buffers, including the project buffer, and this was the planned delivery date of the project. Okay? So you see in this case much higher than the Microsoft project plan duration because of the buffers that have been inserted. If you launch the disruptions now, you see what happens. It's better, definitely better than MS Project, okay? But still, it is not a very stable schedule because the project deadline was not violated. That's good, project did finish in time. But many of the activities were not started according to the plan. So that poor subcontractor was expected to arrive here, while actually he arrived there during the disruptions. Okay? If we do that risk analysis in combination with STC on this example project, what comes out of it was this. A planned duration which is somewhere in between MS Project and ProChain. Okay? And if you launch the disruptions, you see a much more stable schedule. Many of those activities were started exactly according to the plan. Okay? So we are currently testing this out on many of the construction projects. Two conclusions from there. It is still very difficult to convince project managers in Belgium, and I think also in Spain, that what I have been talking about here makes sense. The first reaction is, you are crazy. We don't have the time to do that. That's much too expensive. Okay? I have been doing that for 30 years, and you can tell me to change my behavior. Okay? My people don't understand what you are talking about. What do you mean by inflexibility weight? What do you mean by marginal disruption cost? What do you mean by starting time criticality? Okay? But after a while, some of them, when they see the end result, become more and more convinced that they have been doing things the wrong way. Okay? And it is changing, and that makes me corresponding very glad. Okay, so the idea is to come up with procedures, that's what our research has been about, that generate schedules so that you can protect them against anticipated disruptions in order to increase the stability and in order to decrease your cost overruns and your project delays. There is an extensive list of references. Also in our book, the chapter 9 and 10 deal with that thing, but you know, this book was published in 2002, so many of the things that you find in our book are completely outdated by now. If you need any of those papers, just give me an email and I will be glad to send you that. Questions, ladies and gentlemen? Or do you want to go to that final activity of the workshop? Both? Okay. Any questions? Are you convinced, or do you think that I have been talking nonsense? Because I've been presenting in a rather stochastic way. I mean, we should realize that risk analysis makes sense. Okay? I hate when people say in the construction industry every project is unique. That's bullshit. I mean, if there is a constructing company coming and installing that chair, that will normally not be the first time in history that they did this. Okay? That means there should be an experience in the company saying, okay, if that situation occurs, if I plan that project in December, then there is a high probability that it will be freezing in Belgium, that will be bad weather. You know how the Canadians do that? I went to Canada with a number of Belgian construction companies. And they said when we were in Belgium, we should be very, very, very unlucky here in Belgium because in winter we cannot construct. We have weather delays. And then the guys came in Canada. In Vancouver, there is a ski resort a little bit to the north of Vancouver. Very beautiful, Whistler. And those guys saw a construction company. You know how did they build an apartment building there? There was a huge tent, right, with 4 heaters at the 4 corners of the building site. It was snowing, it was freezing, but there were no weather delays. Obviously this was costly. I mean, you have to erect that tent and then build your house below the tent, right? I mean, your costs will go up. But due to the fact that you managed to keep the project under control, that you finish it on time, with very small delays, those costs are away. They are overcompensated. And suddenly the manager said, okay, in Belgium we are going to construct now buildings under a tent. Ridiculous idea, obviously. Okay? So you see there is a lot of conviction that still needs to go on. No questions? If not, thanks again for your attention. Okay?